The physical properties of alpha amino acid. Amino acids are white crystal solids with high melting points. Amino acids such as glycine and alanine dissolve in water to form neutral solution but have low solubility in organ solvents. These unique properties, which is high melting points and high solubility in water but low solubility in organic solvent, it indicates that the amino acid exists as polar ions. Alpha amino acids are dipolar ions. The term used for dipolar ion is sweeter ion. Please remark that dipolar ions is sweeter ion. So let's look at the zeta ion. Zeta ion is a molecule with an overall charge of 0, which has a positive charge at one part and a negative charge group at another. In neutral solution and in a solid state, amino acids exist as zeta ion. A zeta ion forms when a proton from the COOH group is donated to the NH2 group of the same molecule. For example, in this case, we have the general formula of amino acid. So you can see here, this structure is uncharged structure. Okay. But when after a proton from the COH group has been transferred to the NH2 group, this structure becomes dipolar ion or in the form of zeta ion. However, the molecule has no net charge. As you can see, the total charge here is 0. Neutral amino acids are amphoteric. It can react as acid or base depending on the pH of the solution. So this structure of zeta ion are in neutral. It will be in acidic solution and it becomes cation, which is become acid. We have low pH. The neutral amino acids are amphoteric. It can react as acid or base depending on the pH of the solution. For example, here we have the zeta ion, which is these amino acids are in neutral form. If you react with an acidic solution, so the acidic solution will supply some of the H plus ion. So this H plus ion will be attracted to the parts of the COO negative. So now it becomes COOH. Right? So now the negative charge is disappear and it will give you the positive charge. So now these zeta ion are in the form of cation, which is in acid form and have low pH. If you react in basic solution, the basic solution will give you the OH minus ion. Now the OH minus ion will attract one of the hydrogen from the NH3 plus group and it will give you the NH2 group. So it will leave you with the negative charge of the whole structure. So the structure becomes an anion in the base form and have high pH. So amino acid can exist in three forms depending on the pH of the solution. In neutral, zeta ions are predominant, which is the structure will have two charge here, the negative charge at the COO and the positive charge at the NH3. In acidic form, it will be in K ions, which is K ions are predominates. Okay, now we have only the positive charge. And in basic form, the anions are predominates. We have only the negative charge. Isoelectric point Pi. The isoelectric point is the pH whereby the concentration of Z ion is at maximum and there is equal concentration of both anion and cation. At Pi, the Z ion has no net charge. Each amino acid has its own specific Pi. For example, alanine. The alanine have the isoelectric point at pH 6.02. At this pH, the alanine exists as sweet ion. Let's see some example that involve the isoelectric points, Pi. The isoelectric point of valine 2-amino 3-methylbutanoic acid is 6.0. Predict the structural formula of valine at isoelectric point Pi, pH 12 and pH 1. So, this is the structure of the isoelectric point of 2-amino 3-methylbutanoic acid. You may draw the structure of 2-amino 3-methylbutanoic acid first. Okay, you just follow the name, okay, and then draw it. Okay, standard amino acid structure. Next, to write down, to draw the structure of 2-amino 3-methylbutanoic acid in isoelectric point Pi, we must draw it in the form of sweet ion. Okay, so you may add another one hydrogen for the amino group, and you will lose one of the hydrogen from the carboxylic group. So now these valine are in the form of sweet ion. At pH 12, so we know that the pH 12 are the pH for the basic. In the basic form, so the valine should remove one of the hydrogen from the NH3 plus and become the NH2. So it will become here the NH2 with the neutral parts, and it will leave you only the negative charge of the structure. In another way, that we can say that in pH 12 or in basic structure, it will be in the form of anion. Okay, and then the last one will be at pH 1. So pH 1 is pH that is lower than the Pi. pH 1 is lower than Pi. So it means that this structure of valine will be in the form of acidic. In the form of acidic structure, the COO parts will attract another one hydrogen to give COOH and leave you with the NH3 plus. We can say that these structures are in the form of cation. So let's try this past year's question. Isoleucine 2-amino 3-methylpentanoic acid is an alpha amino acid. Its isoelectric point is 6.0. Draw the structural formula of isoleucine at pH 1, pH 6, and pH 10. Okay, so first let's look at the data given. So it is given that this isoleucine will have the Pi or the isoelectric point at 6.0. So at this moment, this isoelectric point, which is 6.0, is also the pH of the isoleucine at 6.0. Okay, so to solve this problem, okay, draw the structure of the isoleucine first by using its IUPAC names. Okay, so the name given is 2-amino 3-methyl pentanone acid. So this is the structure of 2-amino 3-methyl pentanone acid or isoleucine. Okay, so given the isoelectric point of the isoleucine is 6.0. So at pH 6.0, it will be in the form of zeta ion. Okay, and then pH 1, it will be in acidic solution. And then at pH 10 or greater than the pH 6.0 is in basic solution. So now let's draw the correct structure at the pH given. Okay, so this is the formation of zeta ion of isoleucine, which is at pH 6.0. Right, so you can draw the structure of isoleucine. You must add another one hydrogen for the NH2 group, for the amino group, and then you will lose one of the proton from the carboxylic group. In acidic solution, this zeta ion will have another hydrogen or the H plus ion, okay, and then it will attracted to the COO negative parts. So now the COO negative part will be COOH. Okay, so this one is in the form of acidic, which is pH 1.0. In the basic solution, here we have the OH minus ion. So this OH minus ion will attract one of the hydrogen from the NH3 group, okay, and it will become the NH2 group, okay, and it will give you only the negative charge or in the form of anion. So this is a basic structure for the isoleucine with the pH of 10.0. So that's all for today. Thank you and have a good day.